So here is one more problem at the screen, and this is basically a concept, and it says that so that during an elastic collision, the collision is elastic, not necessarily the head-on collision or the central impact. There is same name for this kind of collision of a smooth balls. That means we are avoiding any kind of spin. The relative velocity is preserved. That is, relative velocity before collision is equal to relative velocity after collision. इलास्टिक कॉलिजन में ऐसा होगा, चाहे कॉलिजन किसी भी टाइप का हो. तो वी नीड टू प्रूव दिस स्टेटमेंट. वी कैन डू इट ऑलवेज. Though some of you won't like to prove this because this is a statement, you would like to take it as a statement. This is true statement, so you can go along with it. But I would like to prove because I am going to use the center of mass frame to prove this, because in ground frame, in lab frame, the things are going to be quite messy. So because in simply in the lab frame you need to assume each and everything, like let the balls having masses m1 and m2 and velocities like v1 and v2 before the impact, and v1 dash and v2 dash after the impact. And then since this impact will not change the total momentum of the system, that means before impact the total momentum is equal to total momentum after impact. And also since the impact is elastic, so you can write that the total and kinetic energy before the impact is equal to the total kinetic energy after the impact. And this will you would like to write simple equations of momentum conservation and energy conservation, like m1 v1 plus m2 v2. And that is not energy conservation equation exactly. This is the conservation equation of kinetic energy, because the collision is elastic. And you would like to write like this for momentum conservation equation. And for kinetic energy you are going to write something like half m1 v1 square plus half m2 v2 square before the collision, and half m1 v1 dash square plus half m2 v2 dash square after the collision. These are the two equations. But if you are going to move on now with these equations, they are going to be quite messy. So I suggest you to learn to work in a frame called center of mass frame, because momentum of the system is conserved. That means velocity of the center of mass of the system is a constant. And you can always write the velocity of the center of mass is simply as m1 v1 plus m2 v2 divided by m1 plus m2. And though I am not going to use it, but I know this is a constant. So let us associate a moving coordinate system with the center of mass of the system. And then, since the center of mass moves with constant velocity, the coordinate system associated with it is inertial. Or you can see that the center of mass frame is a zero momentum frame. So the total momentum of the system before collision is also equal to 0, and after collision the total momentum of the system is also equal to 0 in the center of mass frame, because center of mass frame is itself a zero momentum frame. That means before and after collision in the center of mass frame, total momentum of the system is 0. So 0 equal to 0, writing 0 equal to 0 is not a good practice. So I am going to write down the kinetic energy of the balls in terms of its momentum and mass. And this will do all the things, all the work for us. That is, I am going to write the momentum of mass m1 as p1 bar. And p1 bar by 2 m1, this is the kinetic energy of the mass m1 in center of mass frame. And p2 bar square by 2 m2, this is for ball m2, ball of mass m2, and before collision things are quite clear. And p1 dash square by 2m1, this is the after collision kinetic energy of mass m1, and p2 dash bar square by 2m2, this is the momentum of this is the kinetic energy of the ball 2 after the collision. I would like to write this simply as equation number 2 dash, because equation 2 and 2 dash are same. And you know कि p1 dash and p2 dash, or before collision, the total momentum is equal to 0. That means p1 bar, the magnitude of p1 bar and p2 bar is equal, and they are in opposite direction. And after the collision, the total momentum is also 0. That means p1 dash bar has the same magnitude as p2 dash bar. इन दोनों का magnitude same है, और इन दोनों को यहाँ पुट करें तो यू विल गेट कि p1 बार इज इक्वल टू p1 डैश बार और p2 बार इज इक्वल टू p2 डैश बार इन इक्वेशन 2 डैश. ये तो आपको मिल ही जाएगा. एंड सो दैट इन दोनों का मैग्नीट्यूड सेम है, बट दे आर in opposite direction. So you would like to write the relative velocity before collision as relative velocity of the balls in terms of momentum as p1 bar vector divided by m1 plus p2 bar vector divided by m2. This is not this, but you would like to write in terms of you would like to put a minus sign between them. This is the relative velocity before collision in center of mass frame, and the difference of two vectors in any frame is same. Basically it is independent of choice of coordinate frame. So you can write like here, and you will get the magnitude of relative velocity simply by writing p2 bar is equal to minus p1 bar. p2 bar vector is equal to minus p1 bar vector. So you can put them all together and you will get the magnitude of relative velocity before collision as simply as p1 bar by m1. I am just writing the magnitude plus p1 p2 bar or whatever, p2 bar by m2 as the magnitude. And since p1 bar is equal to p2 bar, so you can write it here p1 bar divided by 1 by m1 plus multiplied by 1 by m1 plus 1 by m2, and this is the relative velocity before collision. In the similar manner you can write the relative velocity after collision as p1 dash bar 1 by m1 plus 1 by m2, and both are same, because you can prove everything from this equation number 2. Exactly, we already know by the concept of zero momentum frame that p1 bar and p2 bar have same magnitude and opposite direction. And similar manner, p1 dash bar and p2 dash bar has same magnitude and opposite direction. If you write all the equations of right hand side in terms of p1 dash bar and left hand side in terms of p1 bar, you will get p1 bar equals p1 dash bar, and you can prove all the things in center of mass frame. Yes, so I have proved it. Thank you very much.